Okay, so this is Lab 11, and this focuses on ANOVA. And ANOVA is an acronym, stands for Analysis of Variance. And we'll see what that means in the course of this lab, and some of the kind of special properties of this test. The main thing, though, is that ANOVA gives us another test that we can use in a scenario or with data that we can't do with the other tests. And in the case of ANOVA, it's going to allow us to use continuous data. So we're looking at group means, just like a t-test. But unlike with a t-test, we can use more than two groups. So we can use three or more groups in an ANOVA. So in that way, it's a bit like a chi-squared test. So you can think about ANOVA as having some of the properties of a t-test and some of the properties of a chi-square test. Now I've already loaded in the data here, and Tidyverse plus a couple of little additional packages here. So we've got CAR for the Levine's test of equal variance. We saw this in the t-test lab. And we've got ggfortify for plotting residuals. Now there's a bit of recoding here, so we're using our date variable again to recode so that we get three groups here for dates. So rather than just January and February, we're going to split up February into post and pre-Valentine's Day using our date variable. So just make sure you've run all of that if you're running through this with me as well. And we should go up to 5 variables, one of which is called period and has our 3 categories. Now, the thing to think about how ANOVA works is that we can use categorical and continuous variables and more than 3 categories. But more than that, one way to look at this is, unlike in chi-squared, where if we have a continuous variable, so we previously used active vehicles, we had to transform those into categories. Right? So we had our sort of cut point of 10,000, and we sort of thought about less than that as low and higher than that as a high active vehicle day, and we looked at proportions. The issue with this is that we're sort of throwing away some of the precision which is in our continuous data. So ANOVA is going to allow us to use our more precise continuous data rather than having to transform it into categories. Now, the final thing with ANOVA, and this is actually something it shares in common with regression, which is the final thing we're going to look at in the Lab 11 optional section, is that it uses this idea of sort of a signal to noise ratio in statistics. And what we mean by that is that all real world data is going to be noisy. It's going to have lots of different sources of variation that mean that it's very rare that we're going to be able to predict or completely account for the variation in one variable with the variation in another. So ideally then we want tests that tell us not only how confident can we be that there really is a relationship between our two variables, but also how much of the variation we've explained, how much signal do we have compared to how much noise. And ANOVA incorporates that in a pretty direct way into how it's calculated. So we're just going to quickly visualize then the situation in which we might use ANOVA. So we've just got a ggplot here, active vehicles and period, and we're going to use a box plot to show this. So if we run this, we should get a box plot that looks a bit like this. So this is the distribution of active Ubers by period. And what you can see is there are some differences between the groups. So in our 3 groups here, we've got These are the medians, but we've got a difference between these groups. But we've also got differences within the groups. So we've got variance within and variance between. And the way our ANOVA is going to work is, it's going to say, what's the ratio of variation explained by the between group differences versus the within group differences? So the within group differences here is the noise, and the between group differences is the signal. So let's have a look at this. So because we're working with continuous data, just like in a t-test, what becomes important is group means. And actually, for 3 groups, we need 4 means. So we need, firstly, the mean of active vehicles overall. We then also need the mean of each of these individual 3 groups. And then finally, we need the variance of those groups for the noise. So I'm going to calculate here what we call the grand mean, the overall mean, and also these statistics. And we're going to save those as stats. So the grand mean and our little table here, these are the statistics that we're going to use to run our ANOVA. And what we then do is we calculate separately what we call the sum of squares between, so between groups, and the sum of squares within groups. And this gives us our signal and our noise. And you can see that for between groups, we're mainly using the differences between these groups and the grand mean. So these are sort of mean differences for each of our 3 group means and the grand mean. What we're using in the sum of squares within is this variance. So we're using the n as well in each, because we want this to be weighted by the size of our groups, which we can see is a bit different. So these 2 groups are 84, and this is 186. We also need degrees of freedom for this test, and those come from, for between groups, the number of rows minus 1 from our stats. So 3 minus 1, degrees of freedom between is 2. And for within, it's the overall number of rows in our data, so 354, subtracting the number of rows in our key stats. So that gives a figure of 351. Finally, then, we're just going to calculate the mean squares using the sum of squares between and the degrees of freedom between, and the sum of squares within and degrees of freedom between. So now what we need is one final test statistic. So just like any other test, this works by generating a test statistic. In this case, we call that the F statistic. And quite simply, this is just a ratio. So it's very literally a ratio between signal and noise. So it's the mean squares between over the mean squares within. So our test statistic is going to be higher the higher mean squares between is, or conversely, the lower mean squares within is. So the higher our signal compared to our noise is going to be a higher F statistic. And all else being equal, that's going to mean a lower p-value and a higher chance that we reject the null hypothesis. And the null hypothesis in an ANOVA is always going to be that means are equal across all 3 periods, or across all 3 groups. So the null hypothesis in an ANOVA, we don't need to give it a direction. It's always that there is no difference between the group means. Our alternative hypothesis then, what we will find is supported if we get a low p-value, is that at least one group mean is significantly different. And note that it only needs one group mean. It doesn't need more than one. And we'll come back to that a bit lower down. So our F statistic then, if we run this, is 1.23. Now we could put this into the relevant distribution. We call this the F distribution. But what we're going to do is we're just going to run some code with the model. So you can see the function here is just AOV. We open this up, we've got our X, our Y, and data. So that's this bit here. So AOV, X variable, Y variable, data. We're also going to save the model here as active period model, and then summarize it to look at the results. So if we run this, here's our model. So it gives us then a few things in this. So here you can see we've got our sum of squares. So our sum of squares between and within. Oh, sorry. This is our sum of squares between and our sum of squares within, and our mean square between and within. Our degrees of freedom that we calculated there, and you can see that's the same F stat we got before. It's just been rounded up a little to 1.24. And that nets out to a p-value of 0.291. So that's not going to be significant under any sort of conventional standard. We'd usually be looking at least below 0.1. So in other words here, we're rejecting our null, we're not rejecting our null hypothesis, we're accepting the null hypothesis that mean active vehicles are broadly equal across groups. And that's sort of what we see here as well. So there's maybe a little bit of a difference here, but not really enough to conclude that this is linked to the number of active vehicles. Now, it's useful to look here as well at running a chi-squared test on this, because this is not the appropriate test. It's continuous data here, active vehicles, so we shouldn't run a chi-squared test. However, if we do, it will work. So here's our chi-square test, and you can see we get a p-value, an x squared, but it's giving us this warning message. Chi-squared approximation may be incorrect. And we can see this because this degrees of freedom is much too high. So in a chi-square test, our degrees of freedom are derived from the x by y table. And so 626 would mean that we've got far, far too many rows or columns in that table. And that's why we're getting this, because probably we have barely any data in most of these squares, because we've used a continuous variable as if it were a category. So that's something that we need to be aware of, that we might be able to run the inappropriate test, and all we'll get is this warning. So we need to look at the warning signs there and switch to an ANOVA if one of our variables here is continuous. Now, if we try to run a t-test, so if I change this, for example, to t-test, now this won't run. So if I try and run this, it's going to tell me exactly what's wrong, that that grouping factor has too many levels. So period has 3 levels. The grouping factor has to have exactly 2 for a t-test. So it just won't run. Now, we're going to come on to some of the assumptions of ANOVA in a minute, but let's just look at one that is going to yield a significant result. And to do that, let's first look at the groups. But let's look at it for trips instead. So our theory here might be that February is going to be a busier month, and maybe particularly leading up to Valentine's Day. But trips is probably a better measure of that kind of demand than is the number of active vehicles. So let's have a see if the group differences are a bit bigger for this. And yeah, it kind of looks like there is, right? There's a bit more difference between the groups here, and a little bit more even spread in within group variation. So let's run an ANOVA on this. So all we need to do is change this to trips. And let's have a look at the model again. So this time you can see we have got a low p-value. And indeed it's telling us that p-value is essentially 0. So we've got these 3 significant stars. And if we compare it to the one for active... oh, no, I've changed the wrong one there. So let's have a look at this again. Trips and period. So let's have a look at this. Yeah, there we go. So we've still got that low p-value. Not quite as significant. We're just under 0.01. Let's compare it to the one for active vehicles. So let's compare the two. So we've got trips here and active vehicles here. So how can we tell that these two, or that this is going to turn out with a low p-value and this with a higher one? Well, firstly, the F statistic, that's higher. So a higher test statistic is going to lead to a lower p-value. But also we can tell in the ratio between the mean square value for the period and the residuals. So the residuals here, this is our noise. Right? This is our from our sum of squares within. And you can see this is 40. This is about 4 times higher than this, whereas this is only just a little bit higher than the noise. So if we compare this figure and this figure, we can tell we're going to get a higher F statistic and a lower p-value than comparing this and this. So that's essentially how to interpret an ANOVA. Okay. Now there's a few additional things that we need to think about here. And one of them is that whenever we have these multiple categories, just as we saw with the chi-square test, we don't know where this low p-value is coming from. Because all that we're testing, remember our H0, is just that at least one of the means is different. So to do this, and I'm actually going to change this to trips because we know there's something significant there. What we do is, instead of our pairwise test of nominal independence, we have in this case a pairwise t-test. And what this gives us is the p-values for t-tests on each of the combinations. Now this looks a little different, but we can see that that's where our low p-value is. It's the comparison of January to post-Valentine's Day February. So again, we can see this in here. That's the significant comparison is between these two groups. The other two comparisons aren't significant. Just this one. We can also use something called the two-key test. And this will give us something similar. So again, we've got p-values here. This was for active vehicles, I think. But we get p-values for each individual test pair. So we could use either of those then, but we have to use something to clarify what's really generating our effect in these three tests. And again, we have these adjustment methods that mean that we can't just get low p-values by just running 20 tests. So this just penalizes us for that and makes the test a little bit more conservative. Now, the last thing then is we do need to be aware of some assumptions here. So all of the tests that we've done in this all have certain assumptions related to the way in which the sample relates to the population, to do with the assumed distribution of the data. Some of these tests, though, have specific assumptions, and one of these is the same as we saw in t-test, the assumption of equal variance. And we have something for that called Levene's test. And in Levene's test, if we get a low p-value, we've failed that assumption of equal variance. So you can see we haven't for active vehicles. Let's check out trips, because that's where our significant result was. Yeah, and we can see we're okay there too. Now, another thing is that we need normally distributed residuals. And this is maybe a little hard to grasp in the context of an ANOVA. When we look at regression next time, I'll talk a little bit more about residuals. But residuals are essentially these differences from the mean of our plotted data. And in theory, for an ANOVA, they want to sort of follow this line. And you can see they don't really here. There's a bit too much of a shape to this. So that's potentially a problem with our model. If we had failed the Levene's test, though, or indeed this one, there are more robust versions of the test. So if we want to run what we call a Welch's ANOVA, you'll remember the Welch's t-test is the more robust one. It's the one we use if we violate the assumption of equal variance. Well, the equivalent for ANOVA is we need to switch away from using AOV, and that instead we run one-way test. And you can see that we can set the variance equal assumption here to false. And it's going to conduct, in that case, one-way analysis of means, not assuming equality of variances. We could likewise run the same for trips. So, there we go. In reality, though, because we know that variances are equal, and we could use one-way test for this as well. So if I set that to true, I just need t for that. So my p-value is a little lower. That'll generally be the case with the classic method. My degrees of freedom is also the same in this case, although it's different here. So in the classic one, it's what we calculated here, 351, and a bit lower for our robust version of the test. So that's ANOVA then. Now again, the key thing really just to remember is the use case. And that use case is that we have a situation like this. We have 3 groups or more. So if we have 2 groups, we can just do a t-test. If we have 3 groups, we need an ANOVA. But we might still need to follow up that with these pairwise t-tests if we do find a significant result. But if we don't, we can just say, well, our ANOVA, has demonstrated that there is no relationship between the group and whatever outcome we're measuring. So in this case, trips. So I'll leave that there with ANOVA. And in the last lab, we're going to look at regression, which is going to allow us to use continuous data with continuous data. And indeed, a regression could also handle groups and continuous data. For that reason, regression is really the most commonly used technique. ANOVA, though, is still used quite a bit in certain fields where we can do experimental controls. So if you read psychological papers, for example, you're likely to still see ANOVAs, sometimes MANOVA, multiple analysis of variance, as a form of testing. So I will see you in the next one where I'm going to talk about regression.